Okay, this might be long. I'm just warning you. But I want to determine the differential equation of motion for a double pendulum. You see the double pendulum appears a lot of places, and you want to model it. So here's how to do that. And there's always more than one way to do this. But I'm going to do the way that makes the most sense to, I think, most people. Now, so what is a double pendulum? Basically, if you had a mass on a string moving in 2 dimensions, that'd be a pendulum. And this is just a pendulum attached to the end of the pendulum. It's a pendulum, double pendulum. Okay, so why is this a difficult problem to model? Oh, let me say, why is it popular? One of the things that's nice about the double pendulum is that you can actually build one of these fairly easily. You can't actually use string because it won't be constrained into 2 dimensions. You'll actually move in 3 dimensions, which is cool too. But then that's not actually what we think of as a double pendulum. What could be done is to have just 2 arms with a pivot. There's not masses on a string, and you get the same kind of thing. And what people like about these, and they actually make these for toys, desktop toys, is that you can start with an initial conditions and then it gets chaotic, and that's kind of cool. Chaos is cool. Okay, so the first approach that you may take to something like this is say, well, that's fine. We can use, Newton's second law or whatever. I have 2 masses, M1, M2, 2 strings, R1 and R2, the initial angle theta1 and theta2. But these also have an x and y coordinates, and I could just say, okay, what if I just use F1, the net force on mass 1 is mass 1 times acceleration 1. Could I not do that? Yeah, I could. And then I could do the same thing for 2. F2 equals M2A2. And now if I draw the masses on M1, here's M1. I have the gravitational force, M1G. And then I have a tension force, I'll call that T2, in the direction of that string right here. And then I have T1 pulling the other way. Now, and then if I do the same thing for the other mass, it's a little bit easier. Here's M2. I have the downward gravitational force, M2G. That's a vector. And then I have T2 pulling this way, whatever way that is. It's the opposite of that, so I'll use the same thing. Even for a simple pendulum, this looks like the equation for a simple pendulum, but it's not, because this tension are very difficult to determine. These are forces of constraint. The force in this string right here is whatever it needs to be in order to keep this mass not from going further than a distance r1 from that point. And this is a force T2 is to make sure that mass 2 doesn't get further away than r2 from mass 1. So there's no equation for it. You can't just write down an equation. So that means that when I write the net force, actually I guess I should write this. I have these tension forces in there. I just don't know what to do with them. I can't write them down as expressions. Yes, in a simple pendulum, you can find the tension by using conservation of energy. But even then, it's not an easy problem. A single pendulum is not an easy problem. Don't let anyone convince you otherwise. Okay, so with that, then we have another way to do this problem. When we have forces of constraints, or we have a problem constrained by motions to where we don't really care about the forces, then we can use the Lagrangian mechanics. So Lagrangian, I'm not going to give a full overview. I'll link to a video down below where I give an overview of Lagrangian mechanics. But it has a couple of advantages. One, I can use whatever coordinates I want. So I don't have to use x and y for these two points. I can use this these theta1 and theta2 for this. With that, if I have any generalized coordinates, I can write the Lagrangian as L equals T minus U, where T is the kinetic energy and U is the potential energy. And that can be in any coordinate system I want. It doesn't have to be the most obvious one. And with that, the equation of motion can be found by minimizing the action integral over time. I think it's over time. And if you want to find the function that minimizes an integral, use the Euler-Lagrange equation, and it says this: the partial of L with respect to one of those variables, qi, minus the time derivative of the partial of that Lagrangian L with respect to qi dot is equal to 0. Now, what the heck is qi dot? again, I'm not going to get into the Lagrangian too much, but we use this dot notation. Qi dot is just the time derivative of Qi with respect to t. And then we can also use Qi double dot is the second derivative of Qi with respect to t. Now, and I'm using Qi as just one of my coordinates. I could have two of them, I could have three. In this case, I'm going to have two. I have 2 degrees of freedom for this particular problem. So I'm going to have theta 1 and theta 2 for the Qi. I'm going to have theta 1 and I'm going to have theta 2. So if I write this down, if I write this equation, I could do it twice, once for theta once and once for theta 1 and 1 for theta 2. Then I can get 2 differential equations of motion. Now, that's going to be harder to solve, but I want to get those 2 differential equations of motion, and that's the goal of this video. Now, I'll go ahead and tell you, my plan is to get 2 differential equation of motions and then stop. And then I'll make another video where I model those 2 differential equation of motions in Python. But that'll be a second video. I just assume this is going to be too long to be one video. Okay, so let's go ahead. I guess I could start right here. I want to write down the kinetic and the potential energies, and that's not easy, right? What, in terms of these variables, it's kind of tough, you know. But if I did Cartesian coordinates, it's not so hard. I can do Cartesian coordinates. I could say t equals 1/2 m1 x1 dot squared plus y1 dot squared, right? That's the velocity of mass 1, plus 1/2 m2 x2 dot squared plus y2 dot squared. That's easy to write. And then I can write the potential energy. Let's call this y equals 0 right there. Then u is going to be m1g y1 plus m2g y2, where those y values will be negative. So that's I can put that in for my Lagrangian, but then I couldn't take the partials with respect to theta 1 and theta 2. So what I need to do is convert these kinetic and potential energy equations into theta 1 and theta 2. And this is a common trick we do in classical mechanics all the time using Lagrangian mechanics. And so the trick I'm going to do is to write an expression for x1 and x2 in terms of theta 1 and theta 2 for both of these, and y1 and y2. Okay, so let's do that. Let's get, I can get x1 right here fairly easily, right? Because if I look, this is going to be x1, this is going to be y1. So I can write that as this. x1 equals r1 sine theta 1. And then y1 is going to be negative r1 cosine theta 1, right? Because it's going to be, if r is a positive number, this is the cosine is going to give me this, but I want to make it negative. Now, what about this mass over here? Well, that one's kind of tricky, right? Because I could do the same thing for r2 and sine theta 2, r2 cosine theta 2. However, that's the position of this relative to that. So what I need to do is to take this and add, to find the x-coordinate of this, it's going to be, let's just write it down, x2 is going to be r2 sine theta 2. But then I need to add on whatever the x-coordinate of mass 1 is, so I need to add that, so it's going to be plus r1 sine theta 1. And the same thing for y2. y2 is going to be equal to negative r2 cosine theta 2 minus r1 cosine theta 1. So now I have those. So I have x and y in terms of theta 1 and theta 2 for both masses. And I can use this because now what I want to do is I want to plug these into these potential and kinetic energy terms. But here you see I have the time derivative of x. So I'm going to need to take the time derivatives of these, square them, and then plug them in. And yes, it's going to get a little messy, but don't worry, it's going to get a lot more messy after that. Okay, so, oops. And you notice I'm using wide paper here because that's how bad it's going to get. Not bad, it's going to get good. It's good. You know, this is a great practice to do these kind of things and keep track of all your terms. It's easy to make a mistake, so you just got to be diligent and check over things. And I'll probably make a mistake. So let's just do it. Okay, let's first take the derivative of x1 dot. So x1, not take the derivative of x1 dot, take the derivative of x1. x1 dot is going to be equal to the derivative of r1 sine theta 1. So r1's constant, but sine is not. So it's going to be r1. Now I need to take the derivative of sine, which is cosine theta 1. But then I need to take the derivative of the stuff in the inside. So I need to take the derivative of theta 1, and that's theta 1 dot. And now I can do the same thing for y1 dot. y1 dot is going to be equal to, it's the derivative of cosine, which is negative sine. So it's going to be r1 theta 1 dot. I'm going to put the theta 1 in the front. I want that one over here, but, sine theta 1. Okay, that wasn't too bad. Let's go ahead and find the kinetic energy term for mass 1. So let's call that T1 is 1/2 m1 times x1 dot squared plus y1 dot squared. So I have x1 dot and y1 dot. I'll just do the square and add them together. Let's do that. So T1 is going to be 1/2 m1. x1 dot squared is this. So it's going to be r1 squared theta 1 dot squared cosine squared theta 1 plus r1 squared theta 1 dot squared sine squared theta 1. Yeah. And you'll notice here that I can factor out r1 squared theta 1 dot squared, and I get this. 1/2 m1 r1 squared theta 1 dot squared times cosine squared theta 1 plus sine squared theta 1. And sine squared plus cosine squared plus sine squared is 1. So now I get T1 is 1/2 m1 r1 squared theta 1 dot squared. And this does have units of actual kinetic energy. It doesn't have to, depending on your generalized coordinates, but in this case it does. And the trig terms drop out, so that's good. And I'm putting a box around it because it's important. Now, I can also write the potential energy for 1. U1 is just going to be m1g y1. Well, I know y1, so it's just going to be negative m1g r1 cosine theta 1. Put a box around it. Okay, now let's do the time derivatives of x2, y2. So let me write those up here, because x2 equals r2 sine theta 2 plus r1 sine theta 1. y2 equals negative r2 cosine theta 2 minus r1 cosine theta 1. So if I'm going to take the derivative of x2, I get x2 dot equals, okay, so here I'm going to get the derivative of sine, which is cosine, and I'm going to have to take the derivative of the inside, which is the derivative of theta 2 is theta 2 dot. So I get r2 theta 2 dot cosine theta 2. Now this one, I'm going to get plus r1 theta 1 dot cosine theta 1. Now for y2, I get y2 dot is going to be equal to, here I'm going to take the derivative of cosine, which is negative sine, so it's going to cancel with that. So I get r2 theta 2 dot sine theta 2 plus r2 theta 2 dot, nope, see, I already made a mistake. r1, I was just in my mind, I was just plowing ahead and I wasn't looking over here. Okay, theta 1 dot sine theta 1. Okay, so you can see here that when I square these terms, I'm going to get 3 terms, right? I'm going to get this squared, and then 2 times this. So, and then the same thing over here. So let's just write out the whole, I got a whole line over here. I can write out the kinetic energy T2. T2 is, see, look, I'm right on the edge. I'm living on the edge. Okay, I'm going to shift this over. There we go. T2 is 1/2 m2. Okay, So now I'm going to square this, so I can square that term. R2 squared theta 2 dot squared cosine squared theta 2. Now I'm going to square that term plus R1 squared theta 1 dot squared cosine squared theta 1. Now I'll get the cross term. So I'm going to get this times this. I'm going to get two of them. So I can get plus 2 R1 R2 theta 1 dot theta 2 dot cosine theta 2 cosine theta 1. Now I need to do this term squared, which I'm going to run out of room. So I'm going to put it down here. I'm thinking ahead. So plus this squared, R2 squared, theta 2 dot squared, that's a dot, sine squared theta 2, plus R1 squared, theta 1 dot squared, sine theta 1 squared. And then I get the twice the cross product, I don't remember what it's called, plus 2 R1 R2 theta 1 dot theta 2 dot sine theta 1 sine theta 2. Okay, so you can see that we get the same thing happening with the sines and cosines. Here I have cosine theta 2 squared, sine theta 2 squared. And so when I factor out the R2 theta 2 dot squared, then I get cosine squared plus sine squared is 1. And the same thing's true over here. Okay, and then I still have this term, which is, I'll have to simplify. But let me write that out. So I'm going to get equals 1/2 m2 R2 squared theta 2 dot squared plus R1 squared theta 1 dot squared. That took care of all these two terms. Now I'm going to factor out this. So I'm going to say plus 2 R1 R2 theta 1 dot theta 2 dot times cosine theta 2 cosine theta 1 plus sine theta 1 sine theta 2. Are we having fun? I mean, it's a lot of work, right? I don't think anyone's going to watch this whole video, but if you're at this point, you're still following along, then welcome and keep with it. I'm telling myself to keep with it. Okay, so now here I have a trick. You know, no one likes tricks, right? But sometimes we just have to use some tricks. So right here, the trick, I'm looking up the tricks. I want to make sure I get the trick right. Okay, so cosine theta 2 cosine theta 1 plus sine theta 1 sine theta 2 is equal to cosine theta 1 minus theta 2. Yeah, so this whole term, you can't see that. So cosine theta 2 cosine theta 1 plus sine theta 1 sine theta 2, that's sloppy, is equal to cosine theta 1 minus theta 2. So that's a little bit nicer. I can put that in right there. Okay, so let's write. Now, the potential energy term is pretty easy because it's just y. So I think we're ready to write down the full Lagrangian, the full thing, with both masses in there. I'm just double checking my notes here. Okay, so L is going to be equal to, I guess I need this piece of paper. Okay, so we have that first kinetic energy term. So it's going to be 1/2 m1 r1 squared theta 1 dot squared plus 1/2 m2. Now this term's a little bit longer, so it's going to be r2 squared theta 2 dot squared plus 2 r1 r2 theta 1 dot theta 2 dot cosine theta 1 minus theta 2 plus r1 squared theta 1 dot squared. That's that other term in there. Now the potential energy term, it's going to be minus the potential, but the potential has a negative sign in there, so it's plus m1 g r1 cosine theta 1 plus m2 g r1 cosine theta 1 plus r2 cosine theta 2. Whew! That's my Lagrangian. I can simplify this some because here I'm going to get 2 cosine theta 1, r1 cosine theta. I can add those two masses together, so that makes it a little bit simpler. So let me just write this over here as just this part as plus m1 plus m2 g r1 cosine theta 1 plus m2 g r2 cosine theta 2. Okay, so that replaces that last term. That way we have, because I don't want to have 3 cosine terms, I'm going to be taking the derivative of, that's one of the variables that can change, where m1 and m2 are constant, so it just makes it a little bit easier. Okay, so now we can start using the Euler-Lagrange equation. So I'm going to start with theta 1. So the Euler-Lagrange equation for theta 1 says this: the partial of L with respect to theta 1 minus the derivative with time of L with respect to theta 1 dot is equal to 0. So let's break this into parts. I'm going to first take the partial of L with respect to theta 1. Partial of L with respect to theta 1. Okay, so now it's a partial derivative. So anything that's not a theta is treated as a constant. I only want to see how this changes with theta 1. So all I care about is theta 1 terms. There's no theta 1 term. No theta 1. No theta 1. Oh, wait, there's one right there. There's a theta 1 term right there. So I'm going to have to take the derivative of this. So I get m2, the 1/2 and the 2 cancel. And then I have all that stuff's constant, but I have to take the derivative of cosine theta, which is negative sine theta. Is it negative? Yeah. So I get negative m2, and then I'm multiplying this by all that stuff. r1, r2, theta 1 dot, theta 2 dot, those are all constants, sine theta 1 minus theta 2, and then I have to take the partial of the inside, which is just 1, right? The partial of theta 1 with respect to theta 1 is 1. Okay, now I'm looking for more theta 1 terms. Theta 1 dot doesn't count. It has to be a theta 1. Here's one right here. So again, I get a minus m1 g r1 sine theta 1. And then here's, I'm sorry, I'm doing down here. So let's put this as minus, it's still the, I'm going to put the minus m1 plus m2 g r1 sine theta 1. And then the derivative of sine theta 1 is theta 1. Okay, now I need to do this term. So I'm going to do this in two parts. I'm going to first take the partial of L with respect to theta 1 dot. Partial of L with respect to theta 1 dot is going to be equal to, okay, I'm going through, there's one right there. So I get, it's a power rule. I can use a power rule. So it's going to bring the 2 down. So I have 2 over 2. So I get m1 r1 squared theta 1 dot. I haven't taken the derivative with time. I'm just doing this part right here. Now I'm looking for another theta 1 dot. Here's one right here. So again, I'm going to multiply 1/2 in there, 1/2 m, and then the 1/2 cancels. And I take the partial of this respect to theta 1 dot, and that just, everything else is a constant. So I get plus m2 r1 r2 theta 2 dot cosine theta 1 minus theta 2. And those are constants as far as that goes, so I don't have to take the derivative of that stuff. It's just a constant. Okay, now I'm looking for another theta 1. Here's one right over here, and that's going to be 1/2. Is that right? 1/2 m1. So that is 1/2. And then I take the derivative, the 2 comes down front, and I get plus m2 r1 squared theta 1 dot. And then there's no more theta 1 dots. Okay, so now I can take the derivative of this with respect to time. Now, in this case, that's a derivative. It's not a partial. So everything that could change with time, I have to take the derivative of. So I'm going to say d dt partial of L with respect to theta 1 dot. Okay, let's go through it. Here's M1 and R1 are constants. They don't depend on time, but this does. So the derivative of theta 1 dot with respect to time is theta 1 double dot. M1 R1 squared theta 1 double dot. Okay, over here I have two terms that, kind of two terms that depend on time. Theta 2 dot and this cosine term. So I need to take the derivative, what's that? The product rule, right? So I need to take the derivative of this times that stuff plus the derivative of this times that stuff. So I get two terms. So I get plus, I'm going to do this one first, M2 R1 R2. The derivative of theta 2 dot is theta 2 double dot. Theta 2 double dot cosine theta 1 minus theta 2. Now I need to take the derivative of this. So I get another plus M2 R1 R2 theta 2 dot. The derivative of cosine theta is minus sine theta 1 minus theta 2. But now I need to take the derivative of the inside, and that's not 1, right? Because I have to take the derivative of theta 1 and theta 2, so I have to multiply this by theta 1 dot minus theta 2 dot. And now this last term is pretty easy because the only thing that depends on time is theta 1 dot, so I get plus M2 R1 squared theta 1 double dot. Okay, so let me check my notes, make sure I'm not missing anything. I'm checking. Theta 1, M1, I have an M1 plus, yeah, so I can combine these two terms here, right? So I have equals M1 plus M2 R1 squared theta 1 double dot. And then I have that term and that term. Plus M2 R1 R2 theta 2 double dot cosine theta 1 minus theta 2 minus M2 R1 R2 theta 2 dot sine theta 1 minus theta 2. You know, I think maybe you could watch this video and like use it to put yourself to sleep. Like I'm just going to fall asleep just listening to someone derive Lagrange's equation for a double pendulum because, you know, I just keep monotonally saying all these variables. Okay, but when I work it out, if I don't say it out loud, I say it aloud in my head because that's one way you got to kind of come up with strategies to keep everything together. Okay, but here is this term. That's the ddt partial of L with respect to theta 1 dot. And then I have this. And so this minus that is equal to 0, so this has to be equal to that. So I'm going to set this whole thing equal to this whole thing. Okay, so long paper out. So I get minus M2 R1 R2 theta 1 dot theta 2 dot sine, and you know we're still on theta 1, sine theta 1 minus theta 2 minus M1 plus M2 G R1 sine theta 1 equals, now my other term, which is M1 plus M2 R1 squared theta 1 double dot plus M2 R1 R2 theta 2 double dot cosine theta 1 minus theta 2. Going to run out of room? No, I'm going to make it minus M2 R1 R2 theta 2 dot sine theta 1 minus theta 2. Whew, I made it. Okay, so I'm putting a box around that. Because this is a differential equation of motion. Let's see if that simplifies. I can't remember. Okay, yeah, it does. So here I have where'd my term with, I dropped off a term. M2, this should have a theta 1 dot minus theta 2 dot attached there at the end of that. So it would have run out of room. But if I do that, if I multiply out this fraction, I'm going to get m1 r1 m2 r1 r2 theta 2 double dot squared cosine theta 1 minus theta 2 theta 1 dot. Okay, and that doesn't do anything. This term is not the same. Aha, but, no, this goes with this term. M1, this is, I messed up on the last case. This has a theta 1 dot minus theta 2 dot. So when I multiply this together, now I'm going to get an m2 r1 r2 theta 1 dot theta 2 dot sine theta 1. And then over here, I have that same thing. So that's going to cancel. I'm just going to be left with the positive version of that with theta 2 dot squared, right? Because I'm going to have that one times another theta 2 dot. So this is what I actually get. I get minus m1 plus m2 g r1 sine theta 1 equals m1 plus m2 r1 squared theta 1 double dot plus m2 r1 r2 theta 2 double dot cosine theta 1 minus theta 2 plus m2 r1 r2 theta 2 dot squared sine theta 1 minus theta 2, right? So that's what happened. The theta 1 term canceled with this theta 1 term. So that's my theta 1 equation. This is really important, and we are going to use this, okay? But we need to go on and do the same equation for theta 2. Okay, so I'm going to write down, we're going to do this. Partial of L with respect to theta 2 minus the time derivative of the partial of L with respect to theta 2 dot equals 0. And once we're done with that, then we'll be done. Okay. So let's do it. I'm going to go back up to my Lagrangian. Let's see if I can do this. There's my Lagrangian right there. Let's see if we can do this. I'm going to put this right here. I'm going to do the partial of L with respect to theta 2 equals. Okay, so now we're just looking for terms that have theta 2 in it. No. And this is a partial. No. Here's one. Okay, so now I'm going to have 1 half m2 times 2, so that the 1 half is going to cancel. So I get m2 r1 r2 theta 2 theta 1 dot theta 2 dot, and I have to take the derivative of cosine theta, which is negative sine theta. So I get negative m2. I don't like writing this on the bottom. Let's just fold this. It's paper. Okay. It's good enough. I know it's not perfect, but it'll work. So negative m2, and then I get r1, r2, theta 1 dot, theta 2 dot, sine theta 1 minus theta 2. And now I have to take the derivative of this with respect to theta 2, and I actually get a negative sign, right? Because the partial of this with respect to theta 2 is negative 1, so it becomes plus. Okay, now what are the terms of theta 2 in it? Here's the theta 2. Oh, actually, I wrote it. I'm using that version right here. So this is the theta 2 over here, and that's actually nice. So I get, again, I get minus M2 G R2 sine theta 2. Putting a box around that. And to double check that I have the right thing. Yeah. Yeah, that looks good. Okay, now I'm going to take the partial of this with respect to theta 2 dot. Partial of L, how long am I? I'm at 35 minutes. Awesome. Partial of L with respect to theta 2 dot. I should leave more room, but I didn't. Okay, let's just do it. No theta 2 dot. Here's 1. So I get, taking the derivative, I get the 2 comes down front, and I get the 2 over 2. So I get M2 R2 squared theta 2 dot. Here's another theta 2. The 2 and this 2, the 1/2 and the 2 cancel. So I get plus M2 R1 R2 theta 1 dot. The derivative of theta 2 dot, or the partial with the L with respect to theta 2 dot, is just 1, so that just goes away. And then I get cosine theta 1 minus theta 2. And I'm looking for more theta 2 dots, and there's no more. Okay, so now I can take the derivative of this with respect to time. I think I have enough room down here. So let's say d dt partial of L with respect to theta 2 dot is going to be, okay, this first term is pretty easy. You notice this term is a little bit easier than the last term because, well, let's just go ahead. So that the only term in this that depends on time is theta 2 dot. So I get M2 R2 squared theta 2 double dot. Now over here I have again 2 terms, so I'm going to take the derivative of theta 1 and I get plus M2 R1 R2 theta 1 double dot, that's a 1, cosine theta 1 minus theta 2. Now I have to take the derivative of this, so I get plus, actually it's minus, actually it's plus. Don't do that, okay? Don't. So I said you're going to take the derivative of cosine, which is sine, negative sine, so it's negative. But then I'm going to have to take the derivative. Oh, wait. Let's just put this as minus. See, good thing I talked myself. Minus M2 R1 R2 theta 1 dot sine theta 1 minus theta 2. And then I need to multiply by the derivative of the stuff inside, which, see, good thing I kept that minus sign there, which is going to be equal to theta 1 dot minus theta 2 dot. That's a theta. Double checking that I got that right. I think so. Wait, there's 3 terms. Yeah, okay. So now I can set this equal to that. More paper. I have a lot of paper so far. Don't worry, there's plenty more. There's plenty where that comes from. Okay, so if I do that, I get M2 R1 R2 theta 1 dot theta 2 dot sine theta 1 minus theta 2 minus M2 G R2 sine theta 2 equals M2 R2 squared theta 2 double dot plus M2 R1 R2 theta 1 double dot cosine theta 1 minus theta 2 minus M2 R1 R2 theta 1 dot sine theta 1 minus theta 2 theta 1 dot minus theta 2 dot done. Putting a box around it. Whew, okay. So, we are finished We are finished. Let me go ahead and rewrite the other. This is an equation that depends. Now, there is a small problem here. Okay, but let me write down the other equation. So the other equation for the theta 1 is negative m1 plus m2 gr1 sine theta 1 m1. I need some water. m1 plus m2 r1 squared theta 1 double dot plus m2 r1 r2 theta 2 double dot cosine. You got, when you say double dot, you go double dot, you got to raise it up because it really makes it more fun. If you just do boring stuff, then it's again boring. Plus m2 r1 r2 theta 2 dot squared sine theta 1 minus theta 2. Oh, this one actually I can make a little bit. I can do the same trick. I forgot. So this is the theta 1 equation, but that is important. So again, I can multiply out this term right here. So I get a theta 1 dot squared term, and then I get a plus m2 r1 r2 theta 1 dot theta 2 dot sine theta 1 theta 2, which is the exact same thing as over in this other side, so it's going to cancel. So I actually get this. Let me see if I can write this out. I get minus, I'm glad I rewrote that, so now I have the two matching pair. Minus 2 m2g r2 sine theta 2 equals m2 r2 squared theta 2 double dot plus m2 r1 r2 theta 1 double dot cosine theta 1 minus theta 2 minus m2 r1 r2 theta 1 dot squared sine theta 1 minus theta 2. Box it. Those are the two. Those are the differential equations of motion for a double pendulum. If you made it, it's 42 minutes. If you made it this far, take this and go this, give yourself a high five, because I'm going to give myself a high five because that's a lot to work through. And I even cheated a little bit because I worked out the solution beforehand because I knew I'd make a mistake. And there still may be a mistake in here. Okay. But the process is important. Okay. So what do we do now? Not in this video. Okay. The problem with this solution is that this term has both a theta. We want the second derivatives, right? Because if you get the second derivatives, you can do a numerical calculation. But it's not ready because this equation has both second derivatives, theta 1 double dot, theta 2 double dot. This one has theta 1 double dot, theta 2 double dot. So I'm actually going to have to solve two equations, two unknowns, to get an expression for theta 1 double dot and theta 2 double dot, and then I can do numerical calculation. But I'm going to do that in the next video. We're going to solve these two, make a solution, a numerical solution in VPython, and animate it, because that's really what you want to do. And so I'm probably going to make at least 3 videos on the double pendulum. So I'll put these in a playlist, and if you have any questions, just let me know. And I'm putting the link down below for the introduction to Lagrangian. I think I might have a couple videos on a pendulum with Lagrangian, and I'll put that down below too, just in case it helps. So congratulations for sticking it through the whole video, and I will see you in the next one.